Hello viewers, in this video we are going to study about the effective mass of electron, which is a direct implication of the chronic penny model, as we have seen that the energy bands are formed due to the motion of electron inside a periodic potential, and these bands already we have seen that they are going to split the E versus K parabola into finite pieces. Now the concept of effective mass arises because of these bands only. Let us assume that there is an electron with total energy E moving inside some periodic potential. As in quantum mechanics, every particle is treated as a wave. Even this electron has an associated matter wave. And let us suppose that the matter wave associated with the electron with total energy E, capital E, being described by E equal to h cross omega, because after all E equal to h nu is the wave waveform of energy. I mean, if a particle is treated as wave, its energy is after all E equal to h nu, the Planck's depicted quantum, or instead of h nu one can write h by 2 pi into 2 pi nu, which is h cross omega. So this is the total energy of the electron if it is considered in the form of its de Broglie matter wave. Omega is the angular frequency or circular frequency of that particular matter wave, right? For some reason, we can simply take the derivative. We can just differentiate this to get dE is equal to h cross d omega. What literally this means is, if you bring a smallest change in the energy of the electron by dE, there will be a change in the frequency of the associated matter wave, the d omega. So if dE change occurs, obviously d omega will be the change in the frequency. So this is what depicted by dE equal to h cross d omega. There is a term called group velocity and also phase velocity in quantum mechanics, where the group velocity actually describes the group of matter waves associated with a moving particle. When an electron is moving, it has a group of waves, matter waves associated, which is sometimes called as a wave packet. So that wave packet has some velocity which is depicted by the group velocity Vg. Actually, this V is representing the group velocity of electron matter wave. The group velocity is given by d omega by dk. This is a standard relation. So that matter wave has a group velocity given by d omega by dk. As we know omega equal to E by h cross, we can simply differentiate this to get d omega equal to dE by h cross. So dE by h cross, and as you know, d omega by dk will be 1 by h cross dE by dk. Similarly, we know the momentum of electron is P, which is given by h cross k. P equal to h cross k. Of course, it is a mass into velocity in classical mechanics. Of course, we call it as h cross k only here. If this electron, let us say it is subjected to some electric field, as E is reserved for energy in this case, we are calling the electric field by letter F. We cannot use E here to avoid confusion. So if F electric field is applied on this electron from outside, it is going to experience a force of minus EF. You know, charge times the electric field is the electric force. So charge is negative electron, so minus E, and electric field is F. So this is going to be the force, and that force according to Newton's law is the rate of change of momentum. We know this dp by dt is representing the change of momentum, rate of change of linear momentum. Of course, this is equivalent to, which is d by dt of p, which is h cross k. So it is h cross coming outside, dk by dt times h cross. This is the term. So dp by dt, wherever you get, we can safely write this. Now coming to acceleration of this electron. Acceleration is of course the rate of change of velocity, the rate of change of group velocity in this case. So this group velocity is dv by dt, and in place of v we can safely replace with d omega by dk, or you can also write this d omega as 1 by h cross dE, and hence this becomes 1 by h cross dE by dk. So d by dt of 1 by h cross dE by dk. As h cross is constant, you can pull it outside, and using chain rule, because it's d by dt and the function is with respect to k, the derivative is with respect to k, so you can write this as d by dk of this into dk by dt using chain rule. So d by dk of this and into dk by dt. So the dk by dt is here, and d by dk of 1 by h cross d by dk is second order derivative, which is 1 by h cross into d square e by dk square. So this is the final term. It is the acceleration. As we know, the dk by dt, which is of course, if you pull this h cross this side, it is actually the force equal to minus ef, as we have already used this. In place of dk by dt in this term, we can put this minus ef by h cross. So we substitute this here, remaining is same. So a equal to this, and if you recall this term, it is actually the force, and this is the acceleration. Force and acceleration, as we know that force is equal to mass times acceleration, this force on the numerator must be h cross times this term. Of course, this h cross comes over here, so this whole term is actually something like inverse of mass, or if you rearrange this, a is going to be minus ef divided by, of course this divided by can be written as a product here. This is so and so, and in the next step what I'll do is I'll write this as some inverse term. You can clearly see here, as you know, force equal to mass into acceleration, or acceleration equal to force by mass. This is force, don't get confused, F is not the force, minus E times of F is the total electric force. So that force divided by something. So if you pull this entire term into the denominator, so it becomes h cross square divided by d square E over dk square. Or by putting simply inverse term here, we can write it like this. As we know, A equal to force by mass. So this mass, of course, we don't call it as mass from now onwards, we call it as effective mass. There is a reason for calling it like this. Normally mass is constant unless we consider the relativistic effects. Usually mass is constant, but here this mass is not constant, and also this mass can be negative also. That's why we don't call it as mass. This is called as effective mass. For the time being, let's treat it as a pure mathematical quantity. So this m star can be written like this, or m star, if you pull this side, it is actually inverse of 1 by h cross square d square e by dk square, or h cross square divided by d square e by dk square is the m star. Please remember this expression. It has some physical meaning. Now we'll make a move to the next article, which is the degree of freedom. See, all these articles are interconnected, so I'll just give the definitions one after the other. There is a term called degree of freedom, Fk. This term is actually representing the degree of freedom. Degree of freedom means the real freedom enjoyed by an electron inside the given solid. If the electron is totally bound, you say freedom 0. If it is completely free, you call it as freedom 1. So you just scale the freedom of electron from 0 to 1. That is what you mean by degree of freedom. And mathematically, this Fk is simply m by m star. So it is the normal rest mass of electron, and this is the effective mass of the electron. So rest mass divided by effective mass of the electron is what you call as degree of freedom. It's just another mathematical function. So we keep this aside and we use them once again. Now let's come to another term called number of electrons in a given band. See, we need all these things because we are going to sketch a graph related to this. That's why my attention is more on all these individual entities. So here, the number of electrons in a given band one can calculate by recalling the right hand side of the Kronig-Penney model. If you recall the right hand side of the Kronig-Penney model, as you know, this is just cos Ka. We took this cos Ka as a +1 or -1, or any value in between +1 and -1. If you observe here, this +1 is cos Ka equal to +1, which means Ka equal to plus n pi. And this -1 is of course another cos Ka equal to cos n pi. So this cos n pi is this Ka. So we can write this as cos Ka equal to plus or minus 1, or Ka equal to plus or minus 2n pi. If we just take the positive sense, then it will be 2n pi. If you take negative sense, it will be just n pi. But In literature, they took Ka equal to 2n pi for some reasons. So this Ka equal to 2n pi, if we take, K becomes 2n pi by A, and n taking integer values. Of course, n0 is not allowed here. Other than 0, values of n, both positive and negative, are taken here. So this is the K. Now, if you simply differentiate this, assuming K and N are variables, dk and dn, if you imagine as variables, are actually, dk is the smallest change in the momentum of the electron indirectly, and dn is the number of electrons within a range n to n plus dn. So this n is actually representing the possible states of electrons within a given band. So for the time being, let's treat it as a mathematical variable. So this k is given by like this expression, and if dk you consider, dk is going to be 2 pi by a times dn, or dn is equal to a by 2 pi times dk. So this is the number of electrons in a given band through an infinitesimal dn. If one has to find out the total number of electrons, simply integrate this expression from the lower number to the top number. If it is 0 and top number is some n, just integrate from that limit, within that limit. And similarly for 0 or lower energy, the k value will be something. The maximum number of electron will be having another k. So between k1 to k2, or minimum k to maximum k of the band, if you integrate, that is going to describe you how many number of electrons exist in that particular band. Of course, here you have to take care of Pauli's exclusion principle, because one state, one n, can be shared by 2 electrons. So this number must be doubled in order to get the single electron states. So just multiply by 2. So this term is going to give you the number of electrons dn which have the momentum or wave vector that lies in between k and k plus dk. So within dk interval of wave vector, this many number of states of electrons are going to exist. Of course, here 2 gone, that's why it is a by pi dk. So please keep these terms in mind: degree of freedom, effective number of electrons inside a given band. Now we'll try to sketch various things as a function of E and K. Of course, as a function of K, we are going to sketch different variables. First, it is E versus K diagram. It's a number of graphs plotted one above the other. So first you focus your attention only on this. So K, and this is the E. This graph is actually this portion. Please observe, only this portion is a little bit exaggerated, so we are only plotting this portion. It is sometimes referred as the first Brillouin zone. So Brillouin zone is extending from minus pi by a to plus pi by a, that is the first zone. Similarly, there is second Brillouin zone which extends from plus pi by a to plus 2 pi by a, and minus pi by a to minus 2 pi by a. So this second part between pi by a and 2 pi by a is called the second Brillouin zone. Similarly, the third Brillouin zone between 2 pi by a to 3 pi by a and minus 2 pi by a to minus 3 pi by a, that is the second Brillouin zone. So there are several zones. Anyway, our discussion is limited only to the first Brillouin zone. So in the first Brillouin zone, if you look at the parabola, or simply if you flip the graph, if you just rotate the graph through 90-degree counterclockwise, whatever that you get is this graph with a little bit zoom. These horizontal lines depicted here are the number of states for electrons. So within on each and every line you can simply put 2 electrons, because one single electron, one particular state can be shared by 2 individual electrons, one with upspin, another one with downspin. So these are the number of states allowed here. It's only a rough diagram. There will be very large number of electrons, as I cannot draw that many. I'm just showing you like this. And one more thing is, if you look at the bottom of the band, see, this is the bottom of the band, the number of allowed states are very less. As you go higher and higher, the lines are getting crowded. So you can expect more number of electrons on the top side of the band compared to the lower edge of the band. So free electrons are available only near the top of the band, but not at the bottom of the band. Of course, I am not saying always free electrons. There may be holes also, which will come in a little moment. So for the time being, you take this parabola. So in this parabola, we are going to see how things are happening. As we said, it is a E versus K. If you take the slope of this graph at this point k equal to 0, it's a horizontal line because you draw a tangent here. It is a horizontal line with respect to the k axis, slope 0. And similarly at the top of this also the slope is 0. So slope 0, and if you take any middle point, the slope is becoming positive. So in this region it is positive, and once again goes back to 0. So there is a point of inflection here where the slope becomes positive, once again decreases, and goes back to 0. So these are some special points which are depicted as k1, of course minus k1 and plus k1 within this minus pi by a to plus pi by a. So this has got some importance. So we are going to see what happens here. So this is the E versus K diagram. That's all. Now we want to know the group velocity. Of course it has no physical meaning, but just we are trying to plot the slope dE by dk. So it is the slope of this graph. So slope of this graph, as already we know that this is 0, this is a positive, and once again it is 0. So if you just sketch it here, slope here is 0, slope here is maximum positive, you can see here, and slope once again became 0 here, like this. So this is the way the dE by dk varies. And symmetrically on the other side also, this is 0 and this is a slope negative. That's why it is maximum negative. You can see it's a minimum, on the negative side it is the maximum, and once again slope came back to 0. So here, so this graph simply depicts the variation of E versus K's slope. Let's take another one, d square E by dk square. Of course we don't really need d square E by dk square, but to know the effective mass, one has to plot this d square E by dk square. D square E by dk square is nothing but the slope of this graph. Slope of this graph is this, slope of this graph is this. You can check it. Here anyway the slope is negative, here the slope is 0. So slope is negative. See, this is the reference axis for d square E by dk square. So here it is negative, it is 0, and at this point positive slope exists. If you draw a tangent here, it is around 45 degree slope, so this is positive. And once again slope becomes 0 here, that's why the curve has dropped to 0, and as the curve is becoming negative sloped, so this function is once again going back to the negative value. So this curve is actually explaining d square E over dk square. Now let's come to the last one, which is m star. M star is nothing but h cross square divided by, there must be one h cross square also, so I should not say equal to. Let me drop this term here. There is a small correction. It should be, yes, okay, let me further adjust this term. Let me do some manipulation. Okay, now I hope it's clear. So it is just inverse of this d square E over dk square. Though h cross square is some term which is negligibly small, of course we depict the variation of graph of m star like this. You don't bother about the multiplicative constant. So d square E over dk square's inverse means you take this graph and take its inverse. Inverse means at every point you have to do 1 by this value. As this is negative in the d square E over dk square, at this point until this point 1 by this negative always negative, and at this point there is a blow, because if you approach from this side it is negative 0, and if you approach from the other side it is positive 0. So just above this point, which is what we call as a point of inflection, there you can see here we have called as a k1 k2, or of course minus k1 here, minus k1 plus k1, symmetric. So at these k1s what's happening is, if you take the inverse of this function, it blows to infinity, positive infinity on one side and negative infinity on the other side, which is depicted by the solid line. You can see here this solid line is going to minus infinity, this solid line is going to plus infinity. And similarly if you take this point and its inverse 1 by this, as this is the largest quantity magnitude wise for this, 1 by this largest is going to be the minimum value. That's why the graph has fallen down here. You can see here, this is the maximum, whereas inverse of this maximum will be the minimum. And once again, on the other side, this graph goes to positive infinity from left hand side, whereas on the other side it goes to negative infinity from the right hand side. So this is one way, this is the other way. And as this is the negative quantity, 1 by negative quantity has some value like this. So this is the surprising graph for the effective mass m star. And surprisingly, the m star is actually going to infinity also in some points. That's why we called it as effective mass. We did not call it as mass, because mass can never be infinity. So this effective mass has some strange behavior at k1. So at point of inflection points, we are going to have infinite mass, means at these points you cannot expect any particle to be filled. So at these boundaries, electrons cannot be occupied in that particular state. That's why there is a huge discontinuity. So please keep this mind, keep in this, please keep these graphs in mind, and we'll make a further move to the next article. Effective number of free electrons in a band. Earlier we called degree of freedom. This degree of freedom is a quantity which describes how far a given electron is free. Free in a sense 0 to 1 scale. If you map fully free, not influenced by anybody, it is 1. Totally bound is what you call as 0. So this degree of freedom has something to do with the effective number of free electrons in a band. We have already calculated number of free electrons in a given band and degree of freedom separately. This is the degree of freedom and this is the number of electrons in a given band. But this effective number of free electrons in a band is a term which tells how many average number of free electrons are really free. For this case, I'll give a simple analogy. Let us suppose that the classroom has tables, benches, which can accommodate 5 students. If you consider a bench where some 5 students are sitting, the students sitting on the edges of the bench have relatively more freedom. That is, if you look at the 5 on the both ends of the bench, the end students, they can either stand up or they can move freely. Whereas the middle 3 students, they don't have that freedom. They can hardly stand, but they can't move unless they are permitted by the neighbors. So you can imagine this situation as the bound electrons in the middle 3. I mean, the 3 middle students can be imagined as a bound electrons with very limited or almost zero freedom. Whereas the electrons or the students who are sitting on the edge of the bench, they can be given 50% freedom, because for both the students they can move in one direction. Means if the table is along x-axis, on one end the particle is free to move along positive x-axis, on the other end the particle or the student is free to move along the negative x-axis. So only 50-50 freedom. The one end cannot move in the positive direction, and similarly the other end cannot move in the negative direction. Only one direction is allowed for them. So 50% freedom. Just like that, inside the band, you can imagine how many number of free electrons are there. If you take the example of 5 students in the bench case, in the table case, hardly 1 unit of freedom is allowed, because if you can imagine the end states as 50-50, means 0.5 freedom, 0.5 freedom, with the remaining 3 students having 0 freedom, the total number of free electrons can be hardly 1 per bench in the case of a bench example. So don't take it too literal, it's only for understanding sake. Now let's come back to this. So number of effective number of electrons, n effective, is nothing but the sum over all the degrees of freedom. So if electron 1 has some quantity of freedom, which is f1, electron 2 has f2, electron 3 has f3, like that, if you add all the degrees of freedom, that is going to describe you how many number of free electrons, effective number of free electrons are there inside a given solid. If there are more number, you call it as a conductor. If they are very less in number, you call it as an insulator. If it is intermediate, you say it's semiconductor. So based on this effective number, one can decide whether a given solid becomes a conductor, a semiconductor, or insulator. Basically, it depicts between conductor and insulator. And if the gaps are finite, we call that particular insulator as a semiconductor. Okay. As you know, this Fk is simply the sum, and we have already derived this Fk as a function of this n. So instead of discrete addition, we go for a continuous summation. So if there are n max number of electrons inside the given solid, inside the given band, so we go from 0 to the maximum electron. So each and every electron will pick up. And what is the freedom associated with each electron? So if Fk is the number of, is the quantity of freedom available with kth electron, of course, the roll number of the electron you may say as some dn. So if you do this summation from the roll number 1 to roll number last of the class, that is going to describe how many free electrons are there inside the given class. Now we are going to calculate this from k1 to k2. k1 to k2 means the lowest wave vector to the highest wave vector for a given band. So these are the limits, and we are simply substituting the Fk. Fk is of course m by m star. M star is this into this dn. Already we have calculated the number of electrons in a band. So the dn is just a by pi into dk. So you substitute it here, a by pi into dk, and integration is going on over k. So a pi can be taken outside, m by h cross square also can be taken outside. And one more thing we have to consider here is k1 is the lower edge of the band, k2 is the higher edge of the band. If you look at this diagram of E versus k, lower, see, electrons can be filled from here to there. So if k1 is the lower one and k2 is the other one, actually k1 and k2 are related to equal and opposite in magnitude. So it is basically k1 equal to minus k2. So instead of integrating from here to here, we can double the integration and we can make the integration from 0 to k. So 0 to k, it is double, because this half is going to give some number, this half is going to give some another number. Some will be this plus this, or instead you can integrate from 0 to this k1 and double that value, because this part and this part are symmetric. So we are doing that. So 0 to k1 m by h cross square, and the rest of the things are very clear. Now this integral, if you look at, this is integration over k and this is this. So you can write this d square e over dk square as d by dk of dE by dk, d by dk of dE by dk, and dk. So dk gets cancelled, and integral derivative also gets cancelled, with upper limit k1 appearing over here, lower limit 0 appearing over here. So it is d by dk with k1 and 0 as upper and lower limits. So this is the n effective for a given band. The surprising thing is, number of effective number of free electrons inside a given solid is just decided by E versus k graph's slope. So just you look at the dE by dk from 0 to the topmost filled band, that will tell you whether a solid becomes a conductor, or it becomes an insulator, or it becomes a semiconductor. You can see here dE by dk. So dE by dk is this graph, or you can take it from here also. dE by dk is 0 at the lower of the band, so you can start from the lower of the band as 0, and dE by dk will be maximum somewhere. Let us suppose that the given solid has a band in which the electrons have filled continuously. Let us say this is the bowl in which you are filling the electrons. So one after the other you have filled the electrons, and fortunately or unfortunately at one point you are out of electrons. So all the electrons are over. So the solid gets filled up to a specific k value, only up to the specific k value, and that value is decided by the atomic number. More the atoms, more the atomic number, more will be the electrons. So you can fill it up to maximum number. Now, if the topmost filled electron has up to k1, then once again here the slope becomes maximum. So this is the slope maximum point, whereas slope 0 point is this, slope 0 point is this. If you have a solid which doesn't have any electrons in the outermost shell, that becomes an insulator. Or if you have a solid which has got electrons filled up to this topmost, here I have filled only half, and if I could have filled up to this point, then that case gives you the topmost filled electrons dE by dk also 0. So bottom of the band dE by dk 0, top of the band also dE by dk 0. So if you have a solid with electrons which are completely filled or completely unfilled in the outermost band, those are what you call as insulators. Clearly this is showing the same. So if you have the k1, the topmost filled electrons k, at the edge of the band, this dE by dk, this becomes 0. So effective number of free electrons is 0, means no free electrons, it becomes an insulator. Whereas if you look at this condition where the topmost electron is filled up to just k1, there the k1 has maximum slope dE by dk here. So this is non-zero and positive. So in this case, you are going to have the d by dk's slope value larger. So in that case, we are going to have effective number of free electrons more, and hence half-filled shells are more likely to become like a metal or a conductor. Completely filled or completely unfilled shells, they behave like insulators. So this classification is now clear on the basis of band theory of solids. So finally, the same explanation is given over here. If the gap between the neighboring bands of an insulator is of the order of 1 electron volt, you call that insulator as a semiconductor. Basically, semiconductor is a kind of insulator. It is a special case of insulator only. So this is regarding the conductor, semiconductor, and insulator. And the last topic of this article is the concept of hole. We have seen the effective mass here sometimes becoming infinity, sometimes becoming positive, sometimes becoming negative infinity and negative. So in the first Brillouin zone, just if you consider from here to here, there the mass of the electron is positive. So mass of the electron becoming positive is quite convincing, but mass of the electron becoming infinity means electrons cannot exist at that particular point. So those electrons do not make any contribution to the electrical conduction. That's what we can consider. Now, mass of the electron becoming negative, this is quite surprising. How can we explain this? Well, to explain this, let's take a closer look on the same effective mass m star. So this d square E by dk square sometimes becoming negative, and hence m star becomes negative. What is m star becoming negative? You apply an electric field from outside. Of course, you can replace this E safely with F to avoid confusion with E, because E is reserved for energy. So let me call the electric field as F. So if a force is applied on, if an electric field of F is applied on the electron, so the m star A, the mass into acceleration, the Newton's second law says this is equivalent to minus EF. Or A, if you take, it is going to be minus EF by m star. If electron is just behaving like electron, this m star would be positive, and hence the acceleration of the electron will be just opposite to that of this F. So if A is in one direction, F will be exactly opposite to that. So acceleration of the electron and the electric field are quite opposite. That is quite normal. But if this m star suddenly becomes negative, then what happens? We'll see here. As A equal to minus EF by electron the effective mass of the electron. So let me replace this F. So it is going to be EF by m star, and hence EE by negative term, which is actually some positive terms times this electric field F. So surprisingly, the electron is going to move not opposite to the electric field, but in the direction of electric field. So acceleration is proportional to F and in the same direction, unlike the opposite direction. So electron is behaving like a positive charge now, because if it's a positive charge, then force, the electric force or the electric field acting on it in the same direction, acceleration will be obtained. F equal to ma will be applicable there. If it is a negative charge, the acceleration will be exactly opposite to that of electric field. So you can clearly convince that this negative effective mass is making the electron to behave like a hole. So what we can understand here is, if you have this empty bowl of solid, you start filling it with electrons one after the other. If you have some solids where the electrons are just filled up to this level, they become excellent conductors. If you have completely filled, they become insulator. If they have no electrons in this, in that case also they become insulators. Now the surprising thing here is, if you have electrons above this K1, means if you start filling it over here, then those electrons will not behave like electrons, but they would rather behave like positively charged holes. So beyond K1, this effective mass becoming negative depicts that on the top edge of this any band you will have holes, whereas at the bottom of the band you always have electrons. I repeat my word once again. In any given band, the top edge of the band, the electrons will behave like holes, whereas at the bottom edge of the band, they behave like just normal electrons. So bottom of the band, negative electrons; top of the band, they behave like holes. Thank you.